Okay, as we start chapter 14, looking at this unit on kinetics, we've had a look at some of the factors that increase the rate of a reaction, and we've talked about what rate of reaction means. We've done chem activity 57 as a POGIL exercise, and you've also looked at you looked at a rate law and the idea of that. So let's just go through these notes. The goals are listed and your learning targets. The idea that molecules need to collide in order to react, and that collision theory indicates you need energy and orientation for the molecules to collide, break bonds, and form new bonds. Now, when we actually look at how rates are affected, we can look at the surface area, we can look at concentration, temperature, presence of a catalyst. That was in the introductory notes that we looked at the beginning of the unit. Okay. Now in the lab, we want to look at these properties of either reactants or products in terms of determining how quickly something is changing in terms of the volume of a gas produced. Gives us an indication of how quickly the products are being formed. In terms of change in mass, how quickly your solid is being lost. Light can be used in calorimetry, titration for concentration or conductivity. When we consider this reaction, we could look at, say, a very simple reaction of A going to B. So we can look at the disappearance of A. That means your concentration final minus initial over time. So A is going down, your final concentration will be smaller. So we have a negative value to indicate it's losing A, and a positive in terms of forming B. So your rate of loss of A is equal to the rate of the gain of B. It's a 1-to-1 ratio. Now, if we look at the idea of average rate, we've talked about average rate here, or instantaneous rate. Your average rate of a reaction is looking at sort of like the change in concentration over a period of time. We don't usually like to have a long period of time because, of course, it's going to change from the beginning where it's going to be quite steep versus the end where it's going to be quite slow. So we have a fast speed happening at the beginning, a slow speed at the end. So over a long period of time, you're taking the average of all of that. So we don't usually want to talk about a long period of time. But then we can get the instantaneous rate by taking the slope of the line, the tangent to the curve. So what you see here is just this idea. If we want to find the rate of the reaction rate at this particular point, then you'd find the slope of that best fit line, rise over run. You don't really need to worry too much about doing this. The AP won't get into so much detail as to ask you to find the slope of the tangent. But just so you know, it's the instantaneous point, or the rate just at that point. Now, if we look at the stoichiometry of rates, let's say that A and B react to give you C and D. So we're going to lose A, and we're going to lose B, and we're going to form C, and we're going to form some D. And we can look at them as fractions like this. I prefer to use conversion factors. So if you know the rate of A, then whatever the coefficient is, B moles, if we want to convert the rate of A to the rate of B, we've got B moles of B to A moles of A according to these stoichiometric coefficients. And same with C. If we want to look at how much C is produced compared to A lost, then we just use conversion factors, C to D, in terms of your C, or C and A Let's just practice that a little bit. So if we have 2 moles of HI, we're going to form 1 mole of H2 and 1 mole of I2. Okay, so we've got twice the loss of HI compared to the formation of H2 or I2. If we look at just an example here, we've got N2O5 is decomposed at this rate, 4.2 by 10 to the minus 7 meters per second. Molar per second, sorry. So if we want to look at the appearance of NO2, we have 4 NO2 to 2 N2O5. So we're just going to use that as a conversion factor here. And so that means that we've got twice as much NO2 forming for every N2O5. So we're going to double this rate to give us the rate of the appearance of NO. It's 8.4 by 10 to the minus 7 molar per second. And O2, half of the O2 compared to N2O5 is formed. So you notice that we use this as a conversion factor in O2. 1 O2 to every 2 N2O5, giving us that rate. Now what you did in the chem activity 57 is that we looked at this idea of a rate law that helps us to say what is the speed of a reaction when you've got certain concentrations of reactants, but notice they're raised to these exponents, and that's what's determined experimentally, and the chem activity helped you to figure this out. So the M and the N exponents are called the orders of the reaction. Okay, so with reactant 1, M is the order with respect to reactant 1 because that's the exponent. And N is the exponent with respect to reactant 2. And remember in the chem activity 57, you found the orders both to be 1 and 1 for the ammonium ion and the nitrite ion. Right. So the overall order is just the sum M plus N. So in terms of the chemistry or the chem activity, you would have had an overall order of 2. Now, again, the experimental determination of them, they've got nothing to do with the coefficients. You cannot use the coefficients to create the order, and we'll talk about that when we get to the mechanism. Now, I mentioned in the chem activity that as you figure out what the value of K is, you really need to consider your units of K. So units are important. They could count for a whole mark in terms of, you have a total of 47 points on the free response question. That could be 1 whole point just for units. So let's go through that. If you have a first order reaction, overall, that means all the exponents have to add up to 1 for first order. So you can only have 1 reactant as changing the rate. So that means your rate law then is, this is a rate law constant K times your concentration raised to the power of 1. So that means your rate would be in units of molar per second. Your concentration is in molar. So when you actually isolate K to get it by itself, that means you're going to bring molar into the denominator, and that means your molars cancel here, and so your units of K are just going to be per second, S to the minus 1. If we have a second order reaction, that means that A could be squared, or you could have 2 1s here in terms of 1 plus 1 giving us a second order overall reaction. So what are our units going to be for that? So we have, again, rate is in molar per second. We have each of the molars multiplied to give us molar squared. So then that goes into the denominator when we rearrange it algebraically. So one of the molars will cancel. We have a molar in the denominator, which becomes M to the minus 1, S to the minus 1, right? And that gives us our units for our rate constant for first order, or second order. What if we had a third order reaction, right? I think that becomes a little obvious then in terms of the pattern. We've got K is equal to, what could we do? We could do A squared, B, that adds up to a total order of 3. So you've got m s to the minus 1 times k times molarity cubed, right, in terms of units. So molarity over molarity cubed, s to the minus 1 is k. That cancels, so m to the minus 2, s to the minus 1 is equal